Hello, and thank you for watching our video for our project on hydrogen production using solar energy. Our team consists of 5 members: Ridley Nahn, Raj Sangha, Alyssa Palazzo, Claire Brewster, and myself, Andrew Rideout.
Our selected process was hydrogen production by a photoelectrochemical cell. In this process, light energy is converted to electricity, which is then converted to hydrogen in one step. The advantages of this process are that it has a low environmental impact and a high efficiency.
Demand for pure hydrogen has tripled since 1975. However, most hydrogen today comes through the reforming of fossil fuels. Governments around the world are pushing for more investment into hydrogen products and production, and specifically the production of hydrogen from renewable energy.
The selected location for our plant is Yuma, Arizona. This is due to a close proximity to the feedstock, as Yuma is at the intersection of the Colorado and Gila rivers, as well as being one of the sunniest places in the world. The capacity for the plant is 1,000 kilograms of hydrogen a day, or 252,000 kilograms of hydrogen a year. Western neighboring states such as California are an ideal market for the hydrogen, and with a new Democratic government doubling down on green energy investment, Yuma, Arizona is the ideal choice.
EC electrolysis produces electricity in a galvanic cell from photons. The electrode configuration consists of a photoanode and a metal cathode. The photoanode is made of a semiconductor that can absorb photons. The energy absorption produces electron holes, causing the water to oxidize, producing hydrogen ions, diatomic oxygen, and a cell voltage. At the cathode, the hydrogen ions are reduced by the electrons carried through the external circuit, forming diatomic hydrogen molecules. A voltage of 1.23 volts must be produced for water splitting to occur. Titanium dioxide is the most researched photoanode for our application. Titanium dioxide exhibits good corrosion resistance properties and produces a cell voltage of approximately 0.8 volts. An external voltage must be supplemented by a photovoltaic cell for titanium dioxide to be used. Further research in materials engineering is required to optimize our process. Other semiconductors can produce a required voltage for water splitting but exhibit poor corrosion resistance. If a semiconductor was used that can harness a wider range of photons in the solar spectrum, a greater voltage could be produced.
The main steps of the process are highlighted in our preliminary block flow diagram. The main inlet of the process, water, is first pretreated before entering the photoelectrochemical device. The PEC cell first absorbs the blue component of the solar spectrum and generates oxygen from water. The DSC cell then absorbs the green and red components of the spectrum, generating the external bias needed for the hydrogen production, which occurs at the counter electrode. The final sections of the process occur after the hydrogen production and is the processing, transporting, and storing of the produced hydrogen and oxygen.
Section 101 is the water pretreatment section. Water is first pumped from the Gila River, at which point it is stored. The water then undergoes preliminary filtration with an activated carbon filter and a micron filter to rid the water of any large solids, microorganisms, or other impurities. The water is then pumped through a reverse osmosis membrane filtration tank, at which 2 streams exit. Stream 105 is the concentrated brine, which is either disposed of or recycled back into the loop, and stream 106 is the clean, permeate stream, which can be used in the photoelectrochemical fields.
Section 200 is the photoelectrochemical field. Each field consists of 1,000 panels that contain 14 cells each. The blue line shows the water entering the field at 25 degrees Celsius and 0.1 megapascals. Inside the cells in the field, sunlight hits the cover of the cell, and the photocathode and photoanode absorb solar radiation. The photoanode oxidizes the water to oxygen, and the photocathode produces hydrogen. The hydrogen in red at 25 degrees Celsius and 0.1 megapascals exits the field through a blower and is transported to a dryer which removes excess water. The hydrogen gas leaves the dryer, passes through a valve, and is transported to the next phase. The oxygen similarly follows this trend.
Section 300 is comprised of the hydrogen gas storage. Following the production of hydrogen in the PEC cell, it enters this section through stream 301 at a temperature of 25 degrees Celsius and pressure of 2 megapascals. The hydrogen undergoes a two-stage compression to achieve a storage pressure around 19.2 megapascals, while maintaining a temperature well below the storage safety level of 52 degrees Celsius in the tanks. The compressors are positive displacement reciprocating compressors operating at a compression ratio of 3.1. Following both compression stages, the hydrogen moves through an intercooler heat exchanger to remove excess heat generated during the compression and is stored at a temperature of 30 degrees Celsius.
400 is our oxygen storage section. Here, oxygen is received from the PEC field at 0.1 megapascals and 25 degrees Celsius. Oxygen is first compressed in a centrifugal compressor up to 0.36 megapascals. The heat generated from compression is removed by a succeeding heat exchanger, cooling the stream back down to 25 degrees Celsius. The oxygen is then ready to be stored as it meets the purity requirements and sits in the appropriate pressure range for medical-grade oxygen requirements.
Some recommendations we have for improving our project in the future is to adjust the angle of the solar panels for maximum solar irradiation, and also the material selection of our tanks so as to combat hydrogen embrittlement.